In this lecture, we look at how to identify the distributions of linear transformations and linear combinations of normal random variables. Here's an outline of what we'll be looking at in this video. We'll first look at the use of linear transformations of normal random variables in statistical inference. We'll then identify the distribution of multiple linear transformations of general multivariate normal random variables. This is in Theorem 1.4. In Corollary 1.4.1, we'll look at a single linear transformation of general multivariate normal random variables and identify its distribution. We'll then look at Corollary 1.4.2, where we identify the distribution of multiple linear transformations of uncorrelated random variables that have the same variance. And then finally, in Corollary 1.4.3, we'll identify the distribution of a single linear transformation, again, of uncorrelated random variables with equal variances. So let's first look at the use of linear transformations of normal random variables in the context of statistical inference. In linear model analysis, we typically compute a number of statistics that are linear transformations of the measured response variables. These statistics are used to develop procedures for making inferences about model parameters as well as for prediction. In particular, they're used in developing procedures for point estimation, confidence interval estimation, hypothesis testing, point prediction, and interval prediction. In order to develop such procedures, we need to understand how these statistics behave probabilistically. Information about the joint probabilistic behavior of these statistics is contained in their joint sampling distribution. In this lecture, we show how to identify the sampling distributions of linear transformations and linear combinations of normal random variables. Next, let's set up the general probabilistic framework that we're going to be dealing with in this lecture. So let bold X be a p×1 vector of random variables possessing a multivariate normal distribution of rank p, so that bold X has a multivariate normal distribution of rank p with mean vector denoted by mu sub x and covariance matrix denoted by cap sig sub x. Now suppose that q new random variables, which we will denote by y1, y2, and so forth up to y sub q, are constructed via linear transformations of the random variables x1, x2, and so forth up to x sub p, where q is no more than p, and the linear transformations are linearly independent. Let bold y be the q×1 vector of these new random variables y1, y2, and so forth up to y sub q. So the question that we're going to be looking at in this lecture video is, what will be the distribution of the random vector bold y? In addition, in what ways will the distribution of bold y be related to the distribution of bold x? We're going to consider this question for several situations. The first result considers the situation where the covariance matrix has a general structure and where two or more random variables are being constructed from the original random variables. So we're going to call this Theorem 1.4, and this is the most general result that we're going to be looking at today. And the other results that we're going to look at are all special cases of this theorem, and that's why they're called corollaries and numbered as special cases of this theorem. So in this theorem, we're going to be identifying the distribution of multiple linear transformations of general multivariate normal random variables. Let X be a p×1 random vector that varies according to a multivariate normal distribution of rank p, where the mean vector for this multivariate normal distribution is denoted by mu sub x, and the covariance matrix is denoted sigma sub x. Next, let bold B be a Q by P matrix of constants of rank Q, where Q is less than or equal to P. And then we're going to use this matrix of constants to define a new random vector, which we'll call bold Y, where bold Y is equal to the matrix B times the random vector X. Then Theorem 1.4 tells us that this new random vector Y has a multivariate normal distribution of rank Q with mean vector denoted by mu sub y and covariance matrix denoted cap sig sub y, where the mean vector of y is given by applying that same linear transformation to the mean vector of x. So the mean vector for y is equal to the matrix B times the mean vector of x. And the covariance matrix of y is equal to B times the covariance matrix of x times B prime. Now note that the mean vector of y is a Q by 1 vector, and the covariance matrix of y is a Q by Q square matrix of rank P. Now the mean vector and the covariance matrix of this new random vector y can be found using two general approaches. The first is to construct each all at once directly using matrix multiplication, using the formulas that we have here. So in particular, the mean vector of y, mu sub y, would be obtained from the mean vector of x by pre-multiplying mu sub x by the linear transformation matrix B, and the covariance matrix of y would be obtained from the covariance matrix of x by pre-multiplying sigma sub x times the linear transformation matrix B, and then post-multiplying that by the transpose of B. The second method is to calculate each entry individually and then piece the entries together to form the appropriate vector or matrix. The next few slides give the formulas for these individual entries. Now, before we proceed, let's introduce notation for the entries in the linear transformation matrix bold B. Denote the entries in the Q by P matrix B as follows. So the linear transformation matrix B has entries that are going to be denoted by lowercase b, and then they're going to be indexed or subscripted according to their row and column in that matrix. So the first row has entries B11, B12, and so forth out to B sub 1p. The second row has entries B21, B22, and so forth out to B sub 2p. And then finally down to the last row, the qth row, the entries are BQ1, BQ2, and so forth out to B sub QP. So the ij entry in this linear transformation matrix B is going to be denoted, and we'll use a couple different pieces of notation here. We'll use the matrix bold B in square brackets and subscript that with I and j corresponding to row I and column j. But we'll typically, or more usually, denote these entries by the lowercase version of the letter lowercase b subscripted with I and j. Now that we have this notation, we can come up with formulas for the entries in the mean vector for y and the covariance matrix for y. The entry in the ith row of the mean vector of y, so mu sub y, is equal to the sum k going from 1 to p of b sub ik times mu sub k. And this is for rows I going from 1 up to q. And so what this means is that the ith entry in the mean vector for y is basically the inner product of the entries in the ith row of the linear transformation matrix B and the entries in the mean vector for x. The entry in the ith row and jth column of the covariance matrix of y, so cap sig sub y, is given by the expression the sum L going from 1 to p and the sum k going from 1 to p of the entries or the terms b sub ik times b sub jl times sigma sub kl. And this is a q by q matrix, and so I and j range from 1 up to q. So with these formulas, we can, if we need to, we can calculate the entries in the mean vector and in the covariance matrix and then put them together appropriately to obtain the mean vector for y and the covariance matrix for y. Now, for a simple example, let's suppose that the random vector x is a 3 by 1 vector that varies according to a multivariate normal distribution of rank 3 with a mean vector of mu sub x, which is a 3 by 1 vector of means, and the covariance matrix, cap sig sub x, is a 3 by 3 covariance matrix of rank 3. Now we're going to denote the entries in the mean vector mu sub x as shown here. So mu1, mu2, mu3, mu1 being the mean of x1, mu2 being the mean of x2, and mu3 being the mean of x3. And the entries in the 3 by 3 covariance matrix of x will be denoted as shown here. So the first row has entries sigma 1, 1, sigma 1, 2, sigma 1, 3. The second row has entries sigma 2, 1, sigma 2, 2, and sigma 2, 3. And then the third row has entries sigma 3, 1, sigma 3, 2, and sigma 3, 3. Now recall the structure, or what these quantities represent in a covariance matrix. So sigma 1, 1 is the variance of x1, sigma 2, 2 is the variance of x2, and sigma 3, 3 is the variance of x3. The off-diagonal elements are the covariances between pairs of variables. And so sigma 1, 2 is the covariance of x1 and x2. Sigma 1, 3 is the covariance of x1 and x3. And sigma 2, 3 is the covariance of x2 and x3. Now, let's define two new random variables, y1 and y2, according to the linear combinations of x1, x2, and x3 that are shown here. So y1 is equal to b11 times x1 plus b12 times x2 plus b13 times x3. y2 is equal to b21 times x1 plus b22 times x2 plus b23 times x3. These two linear transformations can be performed via the matrix transformation shown here. So the 2 by 1 vector of y variables, which we're calling bold y, has the entries y1 and y2, the two random variables. And then we see that that is equal to the 2 by 1 vector containing the expressions on the right-hand side of those two equations in that matrix that we see here. We could represent each of those entries as the sum as shown. And then we could also decompose it as a product of a 2 by 3 matrix, which we're going to call capital B, and a 3 by 1 vector of random variables, which again is x. So these two linear transformations can be represented and performed by this matrix transformation or this matrix multiplication of b times x. So this fits into the framework of Theorem 1.4. Now, according to Theorem 1.4, the distribution of this 2 by 1 random vector y is a multivariate normal distribution of rank 2, and that we get that 2 because we have two linearly independent transformations, the mean vector of which is mu sub y, the covariance matrix of which is cap sig sub y. The mean vector of y is the 2 by 1 vector shown here. So mu sub y, is equal to the linear transformation matrix times the mean vector of x. And so when we carry out that calculation, we see that the entries in that mean vector are the same linear transformations applied to the entries in the mean vector of x. By Theorem 1.4, the covariance matrix of y is the 2 by 2 matrix shown here. So cap sig sub y is obtained by pre-multiplying the covariance matrix of x by the linear transformation matrix B, and then post-multiplying that by the transpose of B. And so when we replace these matrices with their actual entries, as we see here, and carry out the multiplication, we see that we get these formulas, these double summations for each of the entries in this 2 by 2 covariance matrix. And so compare the formulas for the individual entries in mu sub y on the previous slide and cap sig sub y on this slide with the formulas that were given previously. Make sure they match up. We can calculate the individual entries of the mean vector and the covariance matrix and then put them together in the appropriate way to get the mean vector and the covariance matrix for the distribution of y. The next result again considers this question for a covariance matrix with a general structure, but where only one new random variable is being constructed. That is, where Q is equal to 1. Now this is going to be a special case of Theorem 1.4, and so we're going to call this Corollary 1.4.1. And so this is the distribution of a single linear transformation of general multivariate normal random variables. Let x be a p by 1 random vector that varies according to a multivariate normal distribution of rank p with mean vector mu sub x and covariance matrix cap sig sub x. Let lowercase bold b be a 1 by p row vector of constants, shown here, b1, b2, and so forth up to b sub p, and define a new random variable, y, via the linear transformation of x given by y equal to this row vector b times the random vector x. Now this is equal to the sum I going from 1 to p of b sub I times x sub I. And so according to this corollary, which again is a special case of Theorem 1.4, the distribution of the random variable y will be a univariate normal distribution with mean denoted by mu sub y and variance denoted by sigma squared sub y, where the mean of y is equal to the same linear transformation applied to the means of the x's, or applied to the entries in the mean vector of x, and the variance of y is equal to the double sum, I going from 1 to p and j going from 1 to p, of b sub I times b sub j times sigma ij. Now again note that in this context, y is a univariate random variable. It's not a random vector. Now to demonstrate this with a simple example, suppose again that x is a 3 by 1 random vector that varies according to a multivariate normal distribution of rank 3 with mean vector mu sub x, covariance matrix cap sig sub x, with entries as shown here. Now in this situation, we're going to define one new random variable y via the linear combination of x1, x2, and x3 shown here. So y is equal to b1 times x1 plus b2 times x2 plus b3 times x3, or more succinctly, the sum I going from 1 to 3 of b sub I times x sub I. Now this linear transformation can be expressed in vector form as the inner product of this vector that we're going to call lowercase b with the x vector, shown here. Now note that Theorem 1.4 is indeed applicable here with Q equal to 1. And so let's use it in this example and then show that we get the same formulas that we were given in Corollary 1.4.1. So by Theorem 1.4, the distribution of the random variable y is going to be univariate normal, with mean denoted by mu sub y and variance denoted by sigma squared sub y. And the normality result agrees with Corollary 1.4.1. If we apply Theorem 1.40 to obtain the mean of y, then we see that the mean of y is obtained by taking the inner product of this b vector with the mean vector for x. And so we get the sum I going from 1 to 3 of b sub I times mu sub I. And this corresponds to the formula given in Corollary 1.4.1 with p equal to 3. Applying Theorem 1.4 to obtain the variance of y, we see that the variance of y is given by the quadratic form b times the covariance matrix of x post-multiplied by the transpose of b. And so when we expand that out into their particular vectors and matrix, and then carry that calculation out, we see that we get the double summation, I going from 1 to 3, j going from 1 to 3, of b sub I times b sub j times sigma sub ij. And again, this does correspond to the formula given to us in Corollary 1.4.1, where p is equal to 3. The next result applies to the situation where, again, more than one new random variable is being constructed, but where the covariance matrix is a diagonal matrix with equal entries on the diagonal. Now this implies that the random variables x1, x2, and so forth up to x sub p are all pairwise uncorrelated, and that they all have the same variance. Now, by the way, since x1 through xp possess a multivariate normal distribution in this context, the fact that they are all pairwise uncorrelated implies that they are stochastically independent as well. So the next result applies to the following situation. The random variables are all pairwise uncorrelated. This implies that cap sig sub x, the covariance matrix for the random variables, is a diagonal matrix. In addition, the random variables all have the same variance, and so this further implies that the covariance matrix, beyond being a diagonal matrix, has the same entries down the diagonal, and so that common value, which we are denoting by sigma squared sub x, can be factored out of that matrix, and so it has the form sigma squared sub x times the p by p identity matrix. And then finally, we're looking for more than one new random variable being constructed, and so q is greater than 1, and so we're looking for the PDF of a random vector. And so this is Corollary 1.4.2, which gives us the distribution of multiple linear transformations of uncorrelated random variables, all possessing the same variance. So let x be a p by 1 random vector that varies according to a multivariate normal distribution of rank p, with mean vector mu sub x and covariance matrix cap sig sub x, where in this case, the covariance matrix cap sig sub x has a special form equal to sigma squared sub x times the p by p identity matrix. In this case, the x's are uncorrelated and they all have the same variance. Next, let B be a q by p matrix of constants of rank q, where q is less than or equal to p, and define a new random vector via the linear transformation b times x. So we'll call that new random vector y. And then, according to Corollary 1.4.2, which again is a special case of Theorem 1.4, we have that this new random vector y has a multivariate normal distribution of rank q with mean vector mu sub y and covariance matrix cap sig sub y, where the mean of y is equal to the linear transformation matrix times the mean vector for x, and the covariance matrix of y is equal to sigma squared sub x times the linear transformation matrix times the transpose of the linear transformation matrix. Now for a simple example, again suppose that x is a 3×1 random vector that varies according to a multivariate normal distribution of rank 3 with mean vector mu sub x and covariance matrix cap sig sub x, where the entries in the mean vector mu sub x are shown here, mu1, mu2, and mu3, and the covariance matrix has the following form. So it's a 3×3 square matrix with diagonal entries, each equal to sigma squared sub x, and the off-diagonal elements are all 0. Now again, we can rewrite this by factoring out the sigma squared sub x, and so this is equal to sigma squared sub x times the 3×3 identity matrix. So in this case, the x's are pairwise uncorrelated, each with the same variance, which is denoted by sigma squared sub x. Define two new random variables, y1 and y2, according to the linear combinations of x1, x2, and x3 given by the following. So y1 is equal to b11 times x1 plus b12 times x2 plus b13 times x3, and y2 is equal to b21 times x1 plus b22 times x2 plus b23 times x3. Now these two linear transformations can be performed via the matrix transformation y equal to b times x, where y is the 2×1 vector containing the two individual random variables y1 and y2, and then b is the 2×3 linear transformation matrix with entries b11, b12, b13, the coefficients for y1, and the second row contains the entries b21, b22, and b23, which are the coefficients that are used in defining y2. Now again, we can appeal to Theorem 1.4 because it applies here, and this corollary is a special case of Theorem 1.4. And so if we do this, we see that the distribution of this 2×1 random vector y is the multivariate normal distribution of rank 2 with mean vector mu sub y and covariance matrix cap sig sub y. The mean vector of y is the 2×1 vector containing the entries, the sum k going from 1 to 3, b1k times mu sub k, and the second entry is the sum k going from 1 to 3 of b2k times mu k. And that follows from the fact that by Theorem 1.4, the mean vector for y is equal to the linear transformation matrix B times the mean vector for x. Now again, appealing to Theorem 1.4, the covariance matrix of y is the 2×2 matrix obtained by pre-multiplying the covariance matrix of x by the linear transformation matrix B, and then post-multiplying that by the transpose of B. And you can follow the calculations here. When we do this, we see that this is equal to sigma squared times B times the transpose of B. And if we carry out that calculation further, we see here in that last expression, last two expressions actually, nice formulas for the individual entries of that covariance matrix. And so now we would need to make sure that when we calculate those entries, those sums, that we also multiply by sigma squared sub x to get the entry for each position. Now the next result again applies to the situation where the random variables x1, x2, and so forth up to x sub p are all pairwise uncorrelated and they have the same variance. However, in this case, only one new random variable is being constructed. In other words, q is equal to 1. this is what we're looking at here. The next result applies to the following situation. The random variables are all pairwise uncorrelated, and so this implies that cap sig sub x is a diagonal matrix. The random variables all have the same variance, and so that means that the covariance matrix, in addition to being a diagonal matrix, has the same values on the diagonal, and so that common value, which we're denoting by sigma squared sub x, can be factored out, and so we have the covariance matrix being sigma squared sub x times the p by p identity matrix. Only one new random variable is being constructed, and so q is equal to 1 here, and so we're looking for the PDF of a random variable. And so this is Corollary 1.4.3, the distribution of a single linear transformation of uncorrelated random variables possessing equal variances. So let x be a p by 1 random vector that varies according to a multivariate normal distribution of rank p with mean vector mu sub x, covariance matrix cap sig sub x, where cap sig sub x, the covariance matrix of x, has a special structure. It's equal to sigma squared sub x times the identity matrix, and so it's a diagonal matrix with the same entries down that diagonal. And so that implies then that the x sub i's are uncorrelated, all with the same variance, which we denote by sigma squared sub x. Next, let lowercase bold b be a 1 by p row vector of constants, b1, b2, and so forth up to b sub p, and use these constants to define a new random variable y in terms of the x's via the linear transformation of x given by y equal to the inner product of b with x, and that is equal to the sum I going from 1 to p of b sub I times x sub I. Then the random variable y has a univariate normal distribution with mean denoted by mu sub y, variance denoted by sigma squared sub y, where the mean of y is equal to the inner product, that same linear transformation applied to the mean vector of x, and so it's equal to the sum I going from 1 to p of b sub I times mu sub I, and the variance of y is equal to sigma squared times b prime. And so this is the inner product of the b vector with itself. And that turns out to be sigma squared times the sum I going from 1 to p of b sub I quantity squared. Now again, note that in this corollary, because q is equal to 1, y is a univariate random variable rather than a vector. For a simple example, suppose again that x is a 3 by 1 random vector that varies according to a multivariate normal distribution of rank 3 with mean vector denoted by mu sub x, covariance matrix denoted by cap sig sub x, where the entries in the mean vector mu sub x are mu1, mu2, and mu3, and the covariance matrix of x is equal to sigma squared times the 3 by 3 identity matrix, which is the same as the 3 by 3 diagonal matrix with sigma squared sub x in each position on the diagonal. Now, again, in this case, the x's are all pairwise uncorrelated, and they all have the same variance, which we're denoting by sigma squared sub x. We define one new random variable, y, via the linear combination of x1, x2, and x3, as shown here. So y is equal to b1 times x1 plus b2 times x2 plus b3 times x3. This linear transformation can be expressed in vector form as the inner product of this vector that we're calling b with the x vector, where the b vector contains the coefficients for that linear transformation, b1, b2, and b3. And so by Corollary 1.4.3, the distribution of the random variable y is a univariate normal distribution with mean denoted by mu sub y, variance denoted by sigma squared sub y. The mean of y is given by the same linear combination applied to the entries of the means of the x's. So in other words, we take the inner product of the b vector with the mean vector for x. And that turns out to be the sum, k going from 1 to 3, of b sub k times mu sub k. The variance of y is given by sigma squared sub x times the inner product of the b vector with itself. So sigma squared sub x times the sum, I going from 1 to 3, of bi squared. Now, let's look at an important takeaway here. A linear combination of a collection of normally distributed random variables is itself normally distributed. And so that's a very important result that I want you to take away from all this. Next, let's look at the relationships between these various results. So this is a Hasse diagram showing the relationship between theorem 1.4 and the various corollaries. In this diagram, an arrow going from one object, which we'll call B, to another object, which we'll call A, means that object B, or result B, is a special case of result A. And so we see first that corollary 1.4.1 is a special case of theorem 1.4, and it's a special case because in corollary 1.4.1, Q is equal to 1. Corollary 1.4.2 is also a special case of theorem 1.4 because in corollary 1.4.2, the covariance matrix of X has this special structure, this simplified structure, sigma squared sub X times the identity matrix. So it's that diagonal matrix with equal entries down the diagonal. Next, corollary 1.4.3 is a special case of corollary 1.4.1 because in corollary 1.4.3, the covariance matrix again has this special simplified structure of the covariance matrix of X. It's the common variance sigma squared sub X times the identity matrix. And then finally, corollary 1.4.3 can also be thought of as a special case of corollary 1.4.2 in the sense that in corollary 1.4.3, Q is equal to 1. Now, since corollary 1.4.3 is a special case of the other two corollaries, and because each of those corollaries is a special case of 1.4, corollary 1.4.3 is obviously also a special case of theorem 1.4. So that's all I wanted to show you in this lecture video. I'll see you in the next lecture video.